The next plot we are going to generate are heat maps. We are going to use the R package called pheatmap for this. Heat maps are a great way to visualize gene expression data. With heat maps, it's possible to identify groups of genes with similar expression patterns, and you can also use heat maps to identify genes that are commonly regulated. And this also helps to identify signatures that are associated with a particular condition. Heat maps will come or usually come with a color code that can be used to interpret the plot. And so in this tutorial, we are going to plot 3 different heat maps. So I have them listed here. We will plot heat map of sample to sample distance matrix with clustering. Okay, we are going to use the normalized read count. And we're also going to plot a heat map of the log transform normalized read count. And we're also going to plot heat map using z-scores. Okay, so we will start with the first one, which is heat map of sample to sample distance matrix. So to generate the heat map of sample to sample distance matrix, we will first generate the distance matrix. So that will be done using this command. Let me just put a comment here first. So we'll first generate our distance matrix. And for that, we'll use this function. So I'll say sample this, and I'll call the function which is this dist. And then I'll give this other command. So I'll use assay. And then I'll use VSD. That is the variance stabilizing transformation. So this is how we'll do it. This is the first step that we'll use, okay, in this particular activity, that is generating the distance matrix. So I'll run this command, and then the next step will be used to generate the sample distance matrix itself. So I'll say sample this matrix, and I'll say as.matrix. So I'll just use this object, that is sample this. Perfect. So now we have generated a sample distance matrix. Okay, that's what it is. We can also just do this just to confirm. So we can say call names and call sample distance matrix. Okay, that's sample this matrix. So we can do this just to get a column name. So this is what we have to get, okay, because we are plotting the samples. So once we have this, we are ready to go. Okay, so we have this. So what we are going to do next is to set a color scheme. Okay, we will use the color scheme when generating the heat map. So I'll set a color scheme or color code or whatever you want to call it. So I will set a color scheme here. I'm using blues. So I'll say colors, then I'll say color ramp palette. Then I'll give this command here. Let me make sure I have it correct. So I have this, and then I'll say viewer.par and the palettes, and then I'll give some code here. So I have 9 and I have blues. That's what I have here. And then finally, I will say 255. That's the color range. So I'll set this color scheme. I'll leave all useful links in the description box, links that you can also use to do your own plotting. So just check the description box for it. So I have this done. So I'll just execute this command. Okay, so I have set the color scheme. So now I am going to use pheatmap to generate the sample to sample distance matrix. So that will be the next step. So I will say generate the heat map. And then I will say pheatmap. Then I'll specify the distance matrix, the one we generated, which is this one. And then I'll say clustering distance, because we want to cluster. We are going to generate a cluster. We want to add some clustering. So I'll say clustering distance and then I'll indicate the rows equals, and I'll say sample this. That's what I have here. And then I'll use another one here. Let me just go to the next line. I'll say clustering distance. And this time I am going to use columns. So this one here. Okay. And then I will say sample this. And then I'll also indicate the color scheme. So that is this one here. Okay, equals colors. Okay, that's what we have here. So once we are done with this code, we can execute it. So I'll execute it now. Perfect. So now we can see the distance matrix. Okay, so I use blues. That's the color scheme here. So let's take a look at this plot here. I'll enlarge it a bit here. I could have also saved it, by the way, but I just want us to use the R environment. So in this heat map, the color represents the distance between the samples. That's what it means. So the dark blue here that we see, I mean, there's a color. Yeah, let me just state that first. So there's a color scheme here. I use blues. Okay, so we are going to have shades of blues here. I made mention that the sample to sample distance matrix is used to give an overview of similarities and the similarity between samples, okay, with respect to the gene expression data, and we are using normalized counts. So in this particular image here, in this plot here, the dark blue that we see here means a shorter distance. So that means as the color approaches this side here, it's a shorter distance. So the shorter distance means what? High similarity. That's what it means. And so once you have this color scheme, it becomes easy to interpret what you have here. So we can even look at some of the comparisons. So let's look at what we have. So let's take a look at this one here. This is GSM 1180 treated PED. Okay, we have that here. So if you take a look at this, we take a look at this one here, we see that these are similar, okay, based on the color code here. It's around this side here, so it's similar compared to the same sample, okay, and this one here. So this and this, they are similar, but then this and then this, in terms of similarity, this one and this one is less. Okay, so comparatively, you can see that this and this, they are more similar than this sample and then this sample. Okay, and some two are very dissimilar. For example, this one here and then this one here. Okay, so this one again, this one and then this one, they are very dissimilar. Okay, because when you look at the color, it's in this region. Okay, so having this image here helps you to get a general overview of the similarities. That can also help you to tell a good story. It can help you to interpret the data that we are dealing with. So these things, you have to do them because with gene expression data, there is a lot of exploration, and that exploration that you do will reveal the insights, and these insights will help you to answer your biological questions. So that's what we have. Okay, so now let's move on to the next plot. So in the next plot, we are going to use log transform normalize counts. We are going to use the top 10 genes for this one. So let's do that. There is also a heat map, by the way. So let me show you how that is also done. We are now going to get the top 10 genes. The top 10 genes are the most significantly expressed genes. We are going to refer to them as the top 10 hits. So to get the most significantly expressed genes, we will first have to order the seq results. Let's just scroll up to see this. We are going to order the seq result just as we did with this one here. But this time, instead of using p-value, we are going to use the p-adjusted value. Okay, so that means after we have issued this command, the records are going to be arranged in order of increasing adjusted p-value, and then we are going to pick the first 10. Those are the top 10 genes. That's what we are going to do. Because the smaller the p-adjusted value, the more significant it is, or let me just say, the more significantly expressed that gene is. So let's scroll down, and then we are going to perform the activity. So let's start. So let's get the top 10 genes or the top 10 hits. So to do that, we will say top hits, top underscore hits, and then we say equals, and we will say the seq results. We bring our square bracket, we will say order, we bring our parentheses again, and we say the seq results, and we say $p adjusted. Then we will say comma, and then we have our square brackets. After that, we will bring a square bracket again because we want the first 10, the top 10. So 1 to 10, and then comma again. So this is how we will get a top 10 genes. So let's issue this command. And then we want the names. So I'll say top hits equals row.names top hits. I want just the names. So I can just query again. I can say top hits. I want the top 10 genes. So these are the top 10 genes. Okay, so that's what we have. Now we are going to perform the log transformation. And after that, we are going to subset. Okay, we are going to get the records for these genes, the top 10 genes. So let's perform the log transformation. So to perform the log transformation with the seq, we will use the rlog function. Okay, so we will say, let me just bring some comments here first. So I'll say top 10 genes. And now let's look at the rlog transformation. So to get a log transformation using the seq, we will say rld, and I'll say rlog, and I'll say dds blind equals false. So I'll execute this command, and then I'm going to subset and get the records for this. And then after subsetting, I'll call heatmap. So I'll do everything using a one-liner command. So that's what I'll do. I'll say heatmap, and then I'll bring my brackets, I'll say RLD, and then I'll say top hits, and then I'll bring a comma. I can add other options, so I can say cluster rows equals false, show row names equals true, cluster calls equals false. So let's execute this command. Okay, so we will have our heat map given to us. Now this figure here, we have disabled clustering. So if you want to enable clustering, then you can say this. Let's just redo this command here. So if you want to enable clustering, you can just remove these ones here. Okay, by default, clustering is enabled. So we can issue this. So let's execute this command. So if you do that, we are going to get the clustering done for us. Okay. Now, if you have done clustering, then it's also advisable that you add additional information, which we will call annotation. So the annotation will help us know the various groups of these samples. So let's do that. So let's add annotation. So to add annotation, we will do this. We will say df, let me just put it here, df, you can use any name at all. So I'll say df, or let me just say annote info. Let me use this one rather. I'll say annote info as.data.frame, and I'll say call data. And then I'll say DDS. And then I'll bring a square bracket, and then I'll say C sequencing treatments. So let's execute this command. So we have done that. So we are now going to add that information to the plot, the cluster plot. So I'll say this. I'll say P heatmap assay RLD, and then I bring my top hits again, top hits. And then when I come here, I can say, let's just start with this. I'll bring all these again. I'll bring them here. And then I'll say, bring this to another line. I'll say annotation call. That's annotation column equals annote info. So let's execute this command. So if you do that, you will have this popping up. Okay, so this gives some color, and you can use that color to identify the various groups. Okay, the groups, or to, let's say, to identify each sample and then the group that sample belongs to. So that is what we have here. So you can try again, and this time enable clustering. So that is also possible. Now let's continue. Please take note that if you look at other tutorials, it's likely that the criteria for selecting the top 10 genes, or the top 10 hits, or the top hits, okay, will be different. Okay, so what I did here was to show you one way to get a top 10 genes or the top hits. So you can look at what has been done in publications, look at the best practices, and choose the appropriate or an appropriate criteria. Okay, that works for you. So take note of that. Now let's continue. Now we are going to do this. We are going to also generate a heat map of z-scores. So let's do that now. Okay, we are now going to generate a heat map using z-scores. For those who don't know what z-scores are, you can check the Gallery tutorial page. So on the page, just scroll down to this section here. Visualization of the expression of differential expression. So when you click it, you'll be sent to this section. So scroll down a bit, and we are going to find the computation and visualization of the z-score. So I will encourage you to read this information here, and then that will get you started. So for this tutorial, we are going to use a function, an R function, to compute the z-scores and then we are going to select the top 10 genes and then visualize them. So let's go back to the R interface. Okay, so we are on the R interface now. Okay, we are in the R interface. So we are in the R environment now. So I'll create a function, an R function, by the way, that will compute the z-scores. So I'll say cal z score. By the way, this function I got it from Dave Towns blog. I will leave the link to that page in the description box. So I'll just issue this command. So this is the function, then x, and then I'll say x minus mean x, and then we divide by standard deviation. So this is the function. So this will compute the z-scores for us. Okay, so the x here is generic. We are going to place in our data when we call the function. So we have this function done. So we are now going to compute the z-scores. So to compute the z-scores, I'll say z-score all. That means all the genes, the entire data set, the normalized count. That's what we are using. And then I'll say t apply normalize counts. And then 1, and then cal z score. So this will compute the z-scores for us. So after doing that, we will now subset our top 10 genes. We already have our top 10 genes. Okay, remember we have to do that here. So we have them here, top hits. So we are going to subset them here. So I will say z-score subsets, and then I'll say z-score all, and then I will indicate my top hits. So I have that done. So I'll now call p-heatmap. So I'll say p-heatmap, and then I'll specify my z-score subsets. And then I'll use the default settings. So let's execute this command. Perfect. So we have done that. So now we have our z-scores here. Okay, so we are using the top 10 genes. Okay, so once you have this, you can then look at the expression patterns here and then try to make a sense out of what you have. So that's for the z-scores. Okay, now p-heatmap also has an inbuilt function that can be used to compute z-scores and then use the z-scores to generate the heatmaps. Okay, so you can also do that, but I had to use this one because I first had to compute the z-scores for all the genes and then I did a subset. Okay, so that's also possible. Now let's proceed.